Hey guys, go ahead and start by writing down those simple terms from the whiteboards. Pause if you need to. And happy April, happy Easter. It's the day after Easter if you're watching this when you're supposed to be watching it. So we've gotten to the point of the year where we would be doing electrochemistry. Actually, I was still going to tackle some electrochemistry ideas during this Monday lecture. However, after talking with colleagues about what they're doing with the way that the AP exam is leaving electrochem off, I have decided to follow their lead and not fill your brain with some stuff that's definitely not going to be on those FRQs in May. So, as I mentioned in a Schoology posting recently, today's a little different. It's actually a lot shorter than I initially anticipated because the opening of the electrochem and the half reactions is a look at redox reactions, which we did in pre-AP and have not revisited this year yet. But since I'm not going to do the electrochem stuff, I just want to do the revisit part. So what we're going to do is a couple pre-AP skills that you may or may not remember, but you definitely want them in your bag before you take the AP exam. So hopefully this is familiar. And again, this video is shorter than I anticipated due to the cutting out of electrochem. If you looked at our roadmap, though, you'll notice that starting Wednesday of this week, we're going to start our super reviews. So I hope you're copying down all of the slides and preparing to be reviewing the year, since that should be a big focus of ours. There are no slides for you to have copied. That's why you've got these terms, which hopefully you remember. But so two things I just want to visit today is redox reactions. And with redox reactions comes the funky oxidations. In terms of oxidation states, when I say that, you probably think of predicted charges, which most of the time is absolutely true. If I say, what's the oxidation state of oxygen, your brain probably goes straight to -2. And that's almost always true for oxygen. There's most of the elements on the periodic table, their oxidation state and their charge when they're an ion absolutely match each other. But there are some circumstances, some special elements that can have a larger variety of oxidation states. And I just need you to understand how to find those. So if I was going to post slides, this would have been one of them. So here's the rules of finding oxidation states. You can pause if you need to, but you should recognize these rules. And what you'll notice as we go through a couple examples is that I'll absolutely follow them. And usually in a compound, if you're wondering, okay, well, if I'm given this like polyatomic ion, like if you're given dichromate or something, and you're wanting to know the oxidation state of each element in it, there's usually one of them that sticks out that you need to think a little bit harder to figure out because the other two have a constant oxidation state, whereas one of them could have a variety of oxidation states. So let's do a couple practice problems and hopefully that makes sense. And then we'll be going into redox after that. So I'm going to erase this now, the oxidation reduction, but I'll be swinging back to it in a moment. I don't have anything to erase. Okay, so let's start off with nitric acid. So go ahead and write down the formula for nitric acid on your paper. It'd be awesome if you can write it before I do. But nitric acid is HNO3. So the question is, what if I want to know the oxidation state of each element in this compound? Well, there's a couple things that we need to know. We want to keep our rules in mind in regards to the fact that hydrogen is always going to be +1 when bonded. Oxygen is almost always -2 when bonded, but nitrogen is more of a wild card if you look at the rules. The other thing that we need to know is that compounds, unless they are denoted as having a charge, will have a total charge of 0. So keeping that in mind will help me figure out mathematically what charge the elements that can have a variety of charges will have. So what I like to do, if I put this in the simplest steps possible, is I could break the compound up into its elements, all right? Then I'm going to count how many there are in the compound. So we've got 1, 1, and 3. And I'm going to multiply those times their oxidation state. I like to set it up using these squares because I know that the oxidation states, which is what I'm actually looking for, are going to show up in those squares, because sometimes when you're writing different numbers up here, your brain gets jumbled on what the answer actually is. So, all right, now I know that hydrogen is going to be +1 because he always is, and I know that a bonded oxygen in this case is going to be -2, and again, you can look back at the rules on the previous page to verify this, but nitrogen does not have a solid rule in regards to him always being, well, the -3 that you probably assume he is based off his charge. So if I do some simple math here, are you good, baby? Okay. 1 times +1 is +1, all right? 3 times -2 is -6, and I know that I want the total charge of the compound to be what? 0. So then the question is, if I'm going to be taking the sum of everything that's in this compound, what must the nitrogen be? All right, and what you'll notice is that -6 and +1 equals -5, all right? Therefore, the only way to get the -5 to become a 0 is for this to be a +5. All right, you can verify, just add those 3 integers up and they equal 0. Okay, well, 1 times what is +5? And of course, the answer is +5. And now I know the oxidation state of each element in this compound. Yeah, let's do another one. All right, write down the formula for magnesium sulfate. All right, my suggestion is to pause the video and see if you can find the oxidation state of all 3 atoms without my help. I'm going to make my list of Mg, S, and O. I'm going to count that there's 1, 1, and 4. Looking at my rules, I know that magnesium is always +2 and oxygen is always -2. Sulfur, I don't know for sure. 1 times +2 is +2. 4 times -2 is -8. And I know that the total charge of the compound, since it doesn't have a charge dictated, is going to be 0. Now keep in mind, if you're dealing with an ion, right, if it's wanting you to analyze like a polyatomic ion and it's got up here like a -3 charge, well then that just, the only difference is everything would stay the same, but you would want these to equal -3 instead of 0, since it doesn't have a net charge of nothing. -8 and +2 is -6. The only way to make a -6 turn into a 0 is to have a +6. 1 times what is +6? Now, both of my examples here make you not think real hard, but keep in mind that if there was 2 sulfurs here and I was like, okay, well, 2 times what is -6? Well, that alters that number. Make the sentence true. All right, because in that example, it would be what, -3 or +3. But in this case, of course, hello, it is a +6. Stupid words. And now I know the oxidation state of all parties. So why is this important? Well, one of the things that we could have covered in our reactions unit, which was unit 2 from earlier in the year, was redox reactions. The reason we didn't was because electrochemistry uses redox reactions as their base of the entire unit. So it just made more sense to me to just cover everything right there and get your brain going. We're not doing electrochem because they pulled it from the exam. So now I'm just having to make up for it by covering it now, but it's nothing new. Redox stands for reduction oxidation. Basically, in a redox reaction, there's electrons moving around. Based on who is getting rid of, sorry, it's my COVID, who's getting rid of and who's gaining electrons helps you figure out who's being reduced and who's being oxidized. If you look back at the vocab terms from the beginning of the lecture, you'll see that to be oxidized is to lose electrons. Now, make sure you think about what that means. If you're losing electrons, you're losing negatives. If you're losing negatives, you're becoming, that's right, positive. I knew you would know. I knew you would know. Anyway, so the opposite of oxidation is reduction, to be reduced, and the word reduced means to be lessened in our English language, right? But to be reduced is to gain electrons, and gaining electrons makes you negative. So what we're going to do is we'll look at a reaction, we'll track the charges of all species as reactants, compare it to the charge of all species as products, and based on what their charge did, we can know whether they gained or lost electrons, which means we would know whether they were oxidized or reduced. So I'm going to try to get away with only doing one of these. Hopefully I don't make anybody mad, but let's make up a reaction. I'm going to have lithium reacting with strontium nitride. So we're going to go lithium reacts with strontium nitride. All right. I probably wrote too big. That's a single replacement reaction. Lithium and strontium will swap. You don't have to use the activity series on the AP exam if you remember what that is. But I'm going to have to write smaller. I'm sorry. But over here, it's going to be strontium by itself and then lithium nitride. All right, so you should balance the equation because all equations should be balanced, but that's not going to play into our skill here. So I'm not worried about the coefficients right now. All I want to do is be able to track the changes in the species. So I'm going to make a list again, like I did in the tracking the oxidation states, of just the elements that we're dealing with, which is going to be lithium, strontium, and nitrogen. All right. And we're going to want to look at oxidation states on both sides. Now, one of the rules that was on the sheet I held up with oxidation states that we haven't had to mention yet is the oxidation state of a free element. All of the charges that we've been dealing with only come into play whenever we have a compound. All right. If an element's unbonded, all right, a free element like lithium here, oxidation state is automatically 0. So write that real big in your notes, circle it 11 times. All right, a free element always has an oxidation state of 0. So right away, looking at lithium all by himself there, I can say, well, lithium's oxidation state here is 0. Now, as I move into my compound, now I've just got a binary compound here, so it's a little bit easier, but you could go through your steps and you would find out that strontium is going to have a charge when bonded of +2. Nitrogen is going to have a charge of -3. So what I've done here is I have analyzed the reactants. Now, if I take a look at the products and see, okay, well, what are their charges now? I could do a comparison and know what the electrons must have done. So let's do it again. Lithium as a product is now bonded. And if you check out lithium nitride, you'll notice that he's got a charge of +1 as a product. Strontium is now a free element. What's the charge of all free elements? 0. Good job. Nitrogen is bonded, all right, and he was always bonded, all right, and if you look up and if you find out his oxidation state, you'll see it's -3. All right, so now here's where we have to decide if you can apply vocabulary. Lithium went from a 0 to a +1. Therefore, he became more positive. All right, what's the only way to become more positive? What do you have to do with your electrons? Well, you've got to get rid of them. By definition, lithium then was oxidized. All right. Strontium was sitting here positive when it all started off. All right. And when we move to a product side, he's now sitting at 0. So again, just tracking basic charges, +2 down to 0, we've become more negative. Vocab of becoming more negative, reduced. All right. Gaining electrons. That's the only way that we can become more negative. So there it is. Nitrogen was not oxidized or reduced because his charge didn't change. Therefore, the number of electrons he possessed didn't change. And now we've been able to identify, analyze this redox reaction. Now, slightly more annoying thing to end on is that there's a secondary vocab that they can ask for. And again, this is a pre-AP skill. I know you've heard this before. So here's the deal. Whichever species was oxidized is the reason that the other one was reduced, all right? Because he gained the electrons from the other one. So whoever is oxidized is also known as the reducing agent because the oxidized item was in charge of the reducing. Same is true for the other side, all right? If you label an element as reduced, well, that element is the oxidizing agent, which is just the opposite word, right? But for him to be reduced means he had to oxidize the other dude. Here's what I'm saying, is based on the way the question's asked, if we say lithium is oxidized, okay, well, what if the question gave you this and said, what's the reducing agent? What's the reducing agent here? It's not strontium. Strontium was reduced. Who reduced him? Lithium is the reducing agent. Whoever is oxidized is the reducing agent. Whoever's reduced is the dun, 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 oxidizing agent. Again, my intentions for this is for it to be review from pre-AP. There's a chance that this will just be a minimal part of an FRQ in labeling something as oxidized or reduced. I actually highly anticipate it. So you'll want to have a good grip on this. There's Schoology practice, and of course, if you need more help from me, I'd love to help you. Anyhow, I do hope April has started off nice for y'all. I know in most of my videos I say I miss y'all, and you're like, oh, he's just saying that because he's a teacher, but I totally miss y'all. I mean, I miss the pre-AP kids too, but y'all, you AP kids make, y'all are the ones I come home and talk about with my family because I enjoy hanging out with y'all so much. So it sucks that my first year of AP has ended with me not getting to actually hang out in the same room with you guys. And maybe we'll get lucky and get to see each other in May. But if not, I swear if you don't come back and say hello to me next year, I'll lose sleep forever. So anyway, see you Wednesday.